Right now, as you listen to this, you are being bombarded.
Yeah, literally constantly.
I mean, invisible forces are just passing right through the walls of your room, slicing through the air, and, driving directly into your skin.
Which sounds terrifying when you put it like that.
Right. But some of it is completely harmless, while some of it is actively altering your DNA. We
Exactly.
throw around this word radiation all the time, and I feel like it usually instantly conjures up these images of, like, glowing green ooze or hazmat suits or nuclear fallout.
Oh, yeah, the classic sci-fi tropes.
Exactly. So today, for our deep dive, we're using this massive, incredibly comprehensive technical dossier on both ionizing and non-ionizing radiation. And our mission is basically to strip away all those tropes.
Break down what this invisible force actually is.
Yeah, how it interacts with the human body, and, I mean, really how we harness it for everything from, like, the smoke detector on your ceiling to literal space exploration.
So to even understand what's happening in the room around you right now, we have to look at radiation simply as energy, just energy traveling from a source.
Okay.
And it exists on this massive continuous spectrum. It ranges from the visible light you use to read a book to the invisible waves cooking your dinner in the kitchen,
Right.
all the way up to those intense subatomic particles that actually power a nuclear submarine.
I always try to picture this spectrum of energy delivery as having two super extreme ends. On one side, you have energy that just gently warms you up. It acts almost like a cozy thermal blanket.
Yeah, that's a good way to look at it.
But then on the far other end, the energy acts like tiny microscopic wrecking balls just swinging directly into your cellular structure.
And the fundamental dividing line between that cozy blanket and the microscopic wrecking ball is it's a physical mechanism called ionization.
Okay, so what exactly is that?
Well, to understand how ionization works, we have to look at the basic building blocks of your body, which are atoms. You can picture an atom like an onion with a highly dense core.
Right.
At the very center is the atomic nucleus that contains heavy, positively charged protons and neutral neutrons.
And then buzzing around that core in, like, distinct layers or shells are the electrons, right? These incredibly fast-moving, tiny, negatively charged things.
Exactly. And normally, nature insists on a perfect balance. The positive charge of the protons in the center cancels out the negative charge of those buzzing electrons on the outside.
So the atom is stable. It's totally neutral.
Right. But ionizing radiation carries such an extreme amount of raw kinetic energy that when it strikes a stable atom, it physically kicks an electron completely out of its orbit.
Just literally knocks it right into the void.
Yeah, violently ejected. And once that negatively charged electron is gone, the atom's perfect balance is destroyed. It's left with a net positive charge.
So it's not a stable atom anymore.
No, we don't even call it that. It becomes an ion.
Wait, so if I'm, say, walking near a high radiation source, is it the physical microscopic impact of the radiation particle hitting my atoms that actually hurts me? Or is it the aftermath?
Oh, it is entirely the chemical chaos left in the aftermath.
Really?
Yeah. Ions are incredibly chemically aggressive. Because they've been robbed of their balance, they become, like, desperate to react with anything around them just to replace that missing electron.
Oh, wow.
Think of something like hydrochloric acid. It's wildly corrosive, specifically because it contains a massive number of hydrogen ions that are just looking to react.
So they're just tearing things apart looking for balance.
Right. When ionizing radiation forces your stable biological tissue to become aggressive ions, it triggers these violent, high-energy chemical reactions. And those reactions physically destroy the molecules making up your cells. Particularly, and this is the bad part, tearing apart the double helix of your DNA strands.
It's basically molecular Jenga.
That is exactly it.
Like your DNA is a perfectly stacked tower, and kicking out that single tiny electron is like violently pulling out a foundational wooden block at the bottom. The physical pull isn't really what destroys the tower. The biological structure just collapses in on itself because it can't support its own chemistry anymore.
Right. And this brings up a really crucial distinction that people get wrong all the time. Just because an atom has been ionized by this process, it does not mean the atom is now radioactive.
Oh, right. Because radioactivity describes the source that is actually emitting the energy.
Exactly. Ionization is just the biological and chemical damage left in the wake of that energy.
Okay, so now that we know how these these wrecking balls ruin our biological chemistry. We need to look at the actual wrecking crew doing the damage.
The particles themselves.
Right. Particulate radiation. These are forms of ionizing radiation that are actual physical subatomic particles with real mass. And the three main players on this crew are alpha particles, beta particles, and neutrons.
So let's start with alpha particles. They are massive. An alpha particle is essentially the nucleus of a helium atom.
2 protons and 2 neutrons, right?
Yep. Bound together. And in the subatomic world, I mean, that is a massive, incredibly heavy structure. If you look at a cloud chamber, which is a device used to visualize radiation.
Oh, yeah. Those are so cool.
They really are. A central radioactive source emitting alpha particles will leave these thick, dense, fuzzy white trails of ionization. Like, they carve a super heavy path.
But because they're so heavy, they're actually incredibly weak at penetrating materials, right?
Oh, very weak.
I always imagine them as these massive, slow-moving bowling balls. They can only travel maybe a few centimeters in the air.
Exactly. If someone shot an alpha particle at you, it would be completely stopped by a single piece of paper.
Wow.
Or even just the dead outer layer of your skin. It literally wouldn't even reach your living cells.
Which is wild. And we actually use this lack of penetration to our advantage constantly. Like the smoke detector on your ceiling utilizes a tiny amount of alpha radiation.
Yeah, and the particles can't even escape the plastic casing of the detector.
But the medical applications in the dossier were what really stood out to me. Alpha radiation is used in unsealed source radiotherapy to treat cancer.
Yes, it is.
Which at first sounds completely counterintuitive. Like, if alpha particles are so weak they get stopped by a sheet of paper, why on earth are doctors using them to fight aggressive cancer inside the human body?
Because that lack of penetration is exactly what makes it a brilliant medical strategy. Doctors will physically inject a small amount of an alpha source like radium-223 directly into a cancerous tumor.
Right into the center of it.
Right, or into the surrounding bone. The alpha particles act like those heavy bowling balls you mentioned, causing devastating, totally irreparable ionization to the cancer cells that they physically touch.
Ah, I see.
But because they lack any penetrating power, they physically cannot travel far enough to damage the surrounding healthy tissue. The wrecking ball just stays exactly where the doctor puts it.
That is so smart. Okay, so next on the particulate crew are beta particles. If alpha is a bowling ball, beta is a tiny, super fast-moving marble.
A single electron.
Yeah, and the mechanics of how a beta particle is created are fascinating. It happens when a neutron, which has a neutral charge, spontaneously decays inside the nucleus.
It just splits right in two.
Yeah, it splits into a positive proton and a negative electron. The proton stays behind, but the nucleus violently spits out that electron at super high speed.
And that ejected electron is the beta particle because it's, thousands of times lighter than an alpha particle. It has significantly more penetrating power.
So paper won't stop this one?
Definitely not. It will pass straight through meters of air. It'll easily punch right through the dead layer of your skin to ionize living tissue.
So what do you need to stop it?
You need something much denser, like a solid sheet of aluminum or maybe a millimeter of lead. We actually see beta emitters used frequently in industrial settings, like thickness gauges for manufacturing paper or plastics, and in those glowing emergency exit signs that somehow operate without any electricity.
Oh, right. The ones that just naturally glow.
Yeah.
Okay, then we reach the final, and honestly the most intimidating member of the particulate crew, neutrons.
Yeah, neutrons are a whole different beast. They are highly penetrating.
Where do they even come from?
They're typically released during atomic fission, so the splitting of atoms inside a nuclear power plant reactor, or they arrive as high-energy cosmic rays from deep space.
Like outside our solar system entirely.
Exactly. And a neutron will blow straight through 50 millimeters of solid lead without even slowing down.
Wait, so how do you shield against something that just ignores solid lead?
You have to change the shielding material to something rich in hydrogen. Hydrogen actually absorbs the neutron's kinetic energy.
Oh, fascinating.
Thick concrete is effective, but liquid water is actually an exceptional neutron shield. That's why spent nuclear fuel rods are stored deep underwater in highly specialized cooling pools.
Just specifically because the water traps the neutrons.
Yep. Furthermore, neutrons carry this unique hazard called neutron activation. They're so powerful that when they smash into a stable, non-radioactive material, they can become embedded in the nucleus.
Wait, meaning what?
Literally transforming that everyday object into a radioactive isotope itself.
Oh, wow. it makes other things radioactive. That is terrifying.
It's definitely a serious hazard to manage.
Okay, so all three of those, alpha, beta, neutrons, they rely on physical mass to cause damage. But energy doesn't always need a physical form, right?
Right. We can leave particles entirely behind.
And enter the realm of the electromagnetic spectrum.
Yeah.
We're talking about pure waves of radiation moving perfectly straight at the literal speed of light.
Exactly. And the entire electromagnetic spectrum is governed by one absolute rule. Wavelength and frequency are inversely proportional.
Okay, break that down for me.
So picture ocean waves rolling into a beach. The wavelength is the physical distance between two wave peaks. The frequency is how many of those peaks crash into the beach every single minute.
So if the distance between the peaks gets shorter, they'll inevitably crash into the beach much faster.
Right. Shorter wavelength means higher frequency. And most importantly, higher frequency translates directly to higher energy.
Got it. So at the absolute top of that high energy scale, where the waves are incredibly short and furious, we find ionizing electromagnetic radiation.
This is where gamma rays and X-rays live.
And they don't have mass, but they have so much energy, they still act like those microscopic wrecking balls kicking electrons completely out of orbit.
Right, and they are deeply penetrating. Think of a medical X-ray of a human knee joint. It reveals a ghostly silhouette where the radiation passes effortlessly through the soft tissue and muscle.
And it only gets stopped and absorbed by the super high density of the calcium in the bone.
Exactly. Now, the actual damage done to the human body by a gamma ray versus an X-ray is biologically identical.
Wait, really?
Yeah. Once that wave of high-frequency energy hits your tissue, the DNA tearing and the chemical chaos, it's exactly the same. The body literally cannot tell a difference.
But their origin stories are completely different.
Right. We create X-rays artificially. We fire electrons at a metal target inside a vacuum tube. But gamma rays occur completely naturally.
They're emitted from the decaying nucleus of unstable radioactive elements like cobalt-60.
Exactly. But if we move down the energy scale, away from gamma and X-rays, the physical properties shift dramatically. The wavelengths stretch out, the frequency drops, and the energy decreases.
We cross the threshold from ionizing radiation into the non-ionizing realm.
Right. We pass through ultraviolet, down into the tiny sliver of visible light, which is between 400 and 700 nanometers, and then continue down into infrared, microwaves, and finally radio waves.
I always picture the electromagnetic spectrum as a giant grand piano keyboard stretching for miles in both directions.
I love that analogy.
Yeah, but human biology only allows us to actually hear 3 specific keys, right in the exact middle. Our eyes are biologically tuned to an incredibly fractional sliver of visible light. We are completely blind to almost all the light in the universe.
And our inability to perceive the rest of that spectrum often creates this really false sense of security. Because the lower half of the spectrum lacks the brute force to smash atoms and create ions, people just assume it's harmless.
But if non-ionizing radiation can't create chemical chaos, how is it still doing catastrophic damage to the human body?
Because the mechanism of harm transitions. It goes from chemical to thermal and photochemical. It no longer shatters the DNA directly via ionization.
So what does it do?
It literally cooks the tissue, or it causes severe chemical reactions through raw heat and light absorption. Take ultraviolet or UV. It sits immediately below X-rays.
Okay.
It lacks deep penetrating power, so its damage is entirely confined to the surface of the skin and the eyes.
Well, the skin damage is obvious, right? Sunburns, destroying the collagen molecules to cause premature aging, and eventually skin cancer.
Yeah, but the optical damage is brutal. High UV exposure causes photokeratitis. Welders often call it arc eye, and mountaineers call it snow blindness.
Which is literally an agonizing sunburn on the clear surface of your eyeball. That sounds awful.
It is. UV also causes early onset cataracts, perfectly clouding the lens of the eye. And there's also this bizarre hidden respiratory hazard in industrial environments.
Wait, respiratory from light?
Yes. Deep UV radiation, specifically wavelengths below 250 nanometers that are generated by intense arc welding, it physically interacts with the surrounding oxygen in the air.
The actual air itself?
Yeah. The intense light shatters the O2 oxygen molecules. Those solitary oxygen atoms then latch onto other nearby O2 molecules, forming O3.
Wait, so the light literally creates toxic ozone gas out of thin air?
Out of thin air. And it causes severe respiratory irritation for the welder.
That is insane. Okay, so sliding further down our piano keyboard, we hit visible light and infrared. Visible light obviously carries its own risks, like intense blue light can cause photochemical retinal damage, burning the back of the eye without even generating heat.
Right.
But infrared is purely about radiant heat, When you stand near a bonfire or a metal furnace, the heat you feel on your face, that is infrared radiation.
And a thermal camera visually captures this perfectly. In the visual spectrum, a person standing in a room looks completely normal.
Yeah.
But through an infrared lens, human beings glow in bright oranges, reds, and purples because our bodies are actively emitting our own continuous infrared radiation.
Right. And the occupational hazard here is chronic exposure. The dossier mentions glassblowers and foundry workers who stand near molten materials. They absorb massive amounts of radiant infrared heat over decades.
Exactly. The lens of the eye absorbs that heat, slowly cooking over 10 or 15 years, leading to severe thermal cataracts.
Okay, so then at the very bottom of the spectrum, where the waves are incredibly long and slow, we find microwaves and radio waves.
Right.
This includes radar arrays, television broadcasts, and of course, the microwave in your kitchen.
Microwaves cause biological harm purely through internal dielectric heating. They do not ionize, they work by rapidly vibrating water molecules.
Which makes sense. If you rub your hands together really fast, the friction generates heat. A kitchen microwave operates on the exact same principle, but just scaled down to a microscopic level.
Exactly.
The microwave energy forces the water molecules inside your food to flip back and forth billions of times a second. That violent microscopic friction generates the heat that ultimately cooks your dinner.
Now, when human tissue is exposed to powerful industrial microwaves or radar arrays, the body attempts to cool itself down through sweating and blood flow.
Like a radiator.
Right. However, certain anatomical structures have incredibly poor blood supply. The lens of your eye has almost no blood vessels to carry heat away.
Oh, no.
Yeah. So if a radar technician is accidentally exposed to a high-intensity microwave source, the water inside the lens of their eye heats up, cannot cool down, and suffers severe permanent thermal damage.
Which always brings up the question of cell phones, right? Because they operate using low-power microwaves.
Yes, they do.
But the data clearly shows that while standing in front of a high-power military radar dish will undoubtedly cause severe internal burns, the chronic health effects of low-level exposure from a mobile phone remain entirely unproven.
Entirely unproven. The physical energy emitted by a phone is simply too low to cause significant thermal friction in your cellular water molecules.
So we've spent all this time looking at raw, natural emission sources, like a radioactive isotope sitting on a table, a glass furnace radiating heat, or the sun pouring UV down onto a glacier.
Right.
But human engineering totally changed the game by finding a way to take this non-ionizing energy, align it perfectly, and control it, which brings us to lasers.
The word laser is actually an acronym.
I always forget that. What does it stand for again?
It stands for light amplification by stimulated emission of radiation.
Ah.
See, a standard light bulb sends out electromagnetic waves of different lengths, crashing in every possible direction.
It's a chaotic, uncoordinated crowd of people spilling out of a stadium. The light diverges and weakens over distance.
Exactly. But a laser is completely different. The light is coherent.
Coherent, meaning what?
Meaning every single wave is perfectly in phase. All the peaks and valleys of the electromagnetic waves line up in exact synchronization. Furthermore, a laser is non-divergent. The beam does not spread out.
So it's an elite marching band moving in perfect, concentrated lockstep.
That's a great analogy.
And because the beam doesn't diverge, it maintains its intensity across just unimaginable distances. We regularly bounce laser beams off special mirrors left on the lunar surface by the Apollo astronauts.
Oh, yeah. The lunar laser ranging experiment.
Right. The beam travels 250,000 miles to the moon, hits the mirror, and travels 250,000 miles back to Earth, and it stays tight enough to accurately measure the distance. That is mind-blowing.
It is. But that exact non-divergent property makes lasers an extreme biological hazard, specifically to human vision.
Why specifically vision?
Because the biological lens at the front of your eye has one job: to focus incoming light. When a chaotic, divergent light source hits your eye, the lens focuses it into a manageable image.
Right.
But if an already perfectly parallel, highly concentrated laser beam hits your eye, your biological lens focuses that energy down into a microscopic, intensely hot dot directly onto your retina.
So the irradiance is just astronomically high.
Yes. It causes permanent, irreversible blindness in a fraction of a second. You do not even have time to physically blink before the damage is done.
Wow. This has to create a unique problem for occupational safety then, Because with most radiation hazards, like a hot furnace or an X-ray machine, you can utilize the inverse square law.
Exactly. You step back, you put distance between yourself and the source, the energy spreads out, and you are safer.
But you cannot use distance to protect yourself from a laser. Because the beam never spreads out, a high-powered laser is equally capable of blinding you whether you're standing 1 foot away or 100 feet away.
Right. So to survive working in these environments, laboratories rely entirely on engineered controls. Doors are wired with interlocks that instantly cut the power to the laser the exact moment a person turns the handle.
Oh, that makes sense.
The entire beam path is enclosed in metal tubes. Technicians wear specialized optical goggles designed to filter out the exact specific nanometer wavelength of the laser being used while still letting other light through.
But one of the most effective safety measures in the dossier is astonishingly low tech.
The paint.
Yes, painting the entire laboratory in flat matte black paint. Stray, indirect reflections off shiny surfaces, like a discarded metal tool, a glass beaker, or even a wristwatch, are actually one of the leading causes of accidental blindness in laser labs.
It happens so fast. The beam bounces off the watch, hits a technician in the eye, and the retina is burned instantly.
So the matte black paint just absorbs those stray beams, killing the reflections and literally saving eyesight.
It's brilliantly simple. And for the other types of radiation, the rules of protection shift based on the physics. For the wrecking ball particles of alpha and beta or the high-frequency gamma rays, protection means heavy shielding. Lead, water, and thick concrete.
And for intense UV or infrared heat, it means specialized face shields and reflective clothing.
Right. Radiation is not magic. It is not inherently evil. It is merely energy interacting with the physical world, behaving according to strict, predictable mathematical rules of physics.
Which means by understanding those mechanics, the differences in wavelength, frequency, whether or not the energy actually possesses the power to shatter an atom, you can navigate your modern environment with complete confidence.
Absolutely.
Whether you're stepping into a hospital for a medical X-ray, standing near your kitchen microwave, or just walking outside into the summer sun, you now know exactly what that invisible energy is doing the moment it meets your body.
Because it really is just the unavoidable background noise of our planet. Natural radioactivity has existed since the exact moment the Earth formed. It's abundant in the rocks, deep in the soil, and even in the food you eat every day, like the potassium-40 found naturally in bananas. We are constantly exposed to natural cosmic rays washing over us from deep space and terrestrial radiation rising from the ground beneath our feet.
So think about that the next time you walk outside. If early life on Earth evolved while being constantly bathed in this invisible sea of naturally occurring terrestrial and cosmic ionizing radiation, is it possible that these low-level DNA-altering microscopic wrecking balls were actually more than just a hazard? Like, is it possible they actually played a necessary fundamental role in driving the random genetic mutations that sparked human evolution in the first place?
Wow. That's a profound way to look at it.
Right. Maybe that invisible energy isn't just a modern medical tool or an industrial hazard. Maybe it's the very spark that made us who we are.